Hello everyone. This is a continuation of solving problems in elimination reactions. I have already produced one video before this which contains mostly on elimination reactions. We will continue the same because chapters in 22, 23, 24 covers all about elimination reaction. So the reason I am solving this problem is just to reinforce what has been learned in those chapters. So I really encourage you to cover chapters or lectures 22, 23, and 24. And this is part B of the elimination reaction problem solving session. With this, I will continue to solving more problems. So as you see here on the board, there is a reaction which shows an alkene, a terminal alkene, and a doubly substituted, disubstituted alkene converted to a saturated alkanes. Here in this question, it's not more of the reaction. Of course, we'll deal with the reaction. It's a hydrogenation reaction of an alkene, meaning that a hydrogen is being added to the double bond. But the main point is in the question, why are these two reactions? One is highly exothermic, minus 127 kilojoules per mole, and the other is minus 120 kilojoules per mole when the addition is happening. So it all goes to the stability of the alkenes. If an alkene is less stable, it quickly reacts and give off a large amount of heat energy. So the question indirectly is testing your knowledge of the stability of these two alkenes. You don't have to know all these numbers, but by just looking at this, if somebody comes and asks you, this is a hydrogenation reaction, this alkene and this alkene are subjected to the same reaction condition, and you're going to justify why one is highly exothermic, meaning reacts spontaneously than this one. Both react, but one is more exothermic than the other. The explanation is simple. If you just look at this alkene, this is a terminal alkene. Terminal, only monosubstituted alkene. Monosubstituted. This is a disubstituted alkene, meaning that you have alkene on this carbon and alkane on this carbon. But on this one, which is a terminal one, usually all of the terminal alkenes obviously are not alkyl substituted. So if you were to see the stability of these two alkenes, the top alkene is less stable than the bottom one. This is disubstituted according to Saytzeff rules. This should be more stable. That means it reacts less, in less extent. So that's why the top reaction is highly exothermic by 7 kilojoules per mole difference. There is 7 kilojoules per mole difference between these two. So that means the top alkene is less stable than the bottom. So the details on the hydrogenation reaction will come later on in its own chapter as we discover more about alkenes. But the point of this question is to ask you why this reacts with high heat energy and this one is with lesser energy. They are almost the same number of carbon, 1, 2, 3, 4, 1, 2, 3, 4. The only difference on the alkenes is that this is terminal alkene. Structurally, you can write that down as CH2, CH, and you have CH2, CH3. This is the structure of the top alkene. So as you see, this is hydrogen, this is hydrogen, this is hydrogen. So it is only one alkyl chain on it, one alkyl substitution. So that's a monosubstituted alkene. That's why we call it monosubstituted alkene. Hence, it is less stable. Hence, it reacts faster. It doesn't want to stay like this, but the moment it's exposed to some kind of reagent, it should react faster. So this one reacts faster because it is less stable. So that's the answer for this question, even though it's indirect, but it's testing you between these two alkenes, which alkene is more stable. Okay, I will continue more on the alkenes and elimination. Okay, let's continue our problem solving session. Here I have these questions. The main problems here are to identify or to give the products of an E2 reaction, elimination reaction. So when we say E2 reaction, it is a strong, usually strong base, polar aprotic strong bases are used, and the mechanism goes by a single step of abstraction and dehalogenation. So basically, in this set of questions, you are required to give the constitutional isomer, possible alkene products that can be obtained from this. So let's start by just identifying first the alpha carbon and also the beta carbon, where the elimination can happen. So the possibility are for this halide here, this is the alpha carbon, and the beta carbons are and another beta carbon here. So this immediately tells us that there are two isomers, constitutional isomers, as a product of the reaction. So on the beta carbons are obviously the hydrogens. So one of the hydrogens would be abstracted and the halide leaves. That's the mechanism of the reaction. But here I'm not showing a mechanism, but I'll just immediately give you the products of the reaction. One thing you should remember is here is the a tertiary butoxide, a bulky, a strong base. A tertiary, so it could be a sodium or a potassium salt. So this is a tertiary butoxide, a butoxide. So this is very strong base. Whenever you see this, you have to suggest that it is an E2 mechanism as well. But in any case, the products of these reactions are, it's eliminating the dehydrohalogenation. So the first product looks like this. From this beta carbon, you would form, so it's 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, this. So this is one of the alkenes. This, and the other constitutional isomer would be by eliminating one of the hydrogen from this beta carbon. So that would be plus another product, which is this product. So two constitutional isomers. This is a 1 alkene, this is a 2 alkene. That's the position of the double bond, what I'm trying to say is. So this is a 2, 1, 2, 3, 4, 5, 6. A 2, 6. 6 is metal position, but the 2 position would be the alkene. Here you have a 1 position. So that's the 2 possible alkenes. Let's see here. We have this compound. You have the alkyl halide, or the halogen is this DBU. So this DBU is another strong base as well. So whenever you see DBU, you suggest an E2 mechanism. So you have an alpha carbon right here and a beta carbon here. So you only have one beta carbon in relation to this halide. Therefore, you would only have one product, one isomer of an alkene. So it will look like this, 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 this. So the hydrogen that would be eliminated would be this hydrogen from the beta carbon, and the halide is this. So minus you have with HCl. That means that's what is being eliminated. Okay, this is the only product. In this case, you have a tertiary. Sometimes you should also remember what kind of alkyl halide it is. This is a secondary alkyl halide because it's only secondary. A secondary one gives more than one product. Here you have, this is also a primary alkyl halide. We are referring to the alkyl halide. This is primary. Here you have a tertiary one because the iodide is on this carbon, which is substituted at 3 different carbons. So it has more than one, obviously, beta carbon. So the alpha carbon is this, but you have this beta carbon, and this beta carbon. Remember, you have 3 different beta carbons from which the hydrogen can be eliminated. So those are three possible elimination products. That means 3 different products we get. Another comment I want to give here is the hydroxide anion is also, for example, if it was sodium hydroxide, potassium hydroxide, these are strong bases. So this is also, that's why it is an E2 mechanism. So let me list down all the 3 possible products. So you have this CH3, which is that CH3. This is one product. Okay. The other product would be plus, when you are losing one of the hydrogens from this one, you would get that product. So the first one is by losing from here. The second product is by losing the hydrogen from this. Now we are going to do it from this beta carbon as well. So the third one would be this is the third one. 3 different alkenes. Remember, 3 beta hydrogens possible, 3 different constitutional isomers. These are constitutional isomers. Okay, let's do this one. This is tertiary butoxide as well, strong base. Let's see how many beta carbon we have. Alpha carbon, this is a beta carbon. No other beta carbon in relation to this carbon. So this should give only one product, which is this product right here. Is the only product because you have only one beta carbon which has one possible beta hydrogen. Let's see this one. On this one, this is your alpha carbon, this is your beta carbon, this is your beta carbon. 2 products are possible because you have 2 beta positions or hydrogens that can be taken out. So the possibility 1, if we just do from this one, we'll get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is one of the products. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is by losing from these hydrogens, one of these hydrogens. If you will lose from this one, we get the following compound. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So that is another one by losing from this beta carbon. So this is a beta carbon. That's 2 hydrogens. One of the hydrogens would be used. You get that product as well. So 2 constitutional isomers. Let's finalize with this one. As you see here, this is the alpha carbon, but there are 2 beta hydrogens or beta positions. This is one beta. They are different from this one, so this is another one as well. So this obviously is hydroxide, a strong base. The 2 products would be one of the elimination. If you just eliminate from this, you would get this, and this is a product. If you eliminate from this top, you would get this. These are completely different because these dimetals are close to this. The dimetals are far. So these are obviously 2 different constitutional isomers. So basically, what we have studied in this is you need to see where the alpha carbon is relative to that alpha carbon positions where there are beta hydrogens. Are possibilities for elimination. So all you produce are different constitutional isomers. So this is an E2 reaction because all of these are strong bases. So we'll continue more on this. Here there are questions. These 3 compounds are given as a product. That means these are the alkene products generated from an alkyl halide. If you have an alkyl halide, if you treat it with a strong base, or if you do E2 reaction, you'd produce an alkene. So the question here is a reverse. They're asking you, what alkyl halide would you use to produce this as only product, without any competition for any other isomers, constitutional isomer? That means the position where the hydrogen and the halide would be is important. So, for example, for this one, if you suggest an alkyl bromide, for example, this could be made from CH3 to CH at that point, and CH2Br or Cl. You could suggest this. That means this is the alpha carbon, this is the beta carbon. If you just eliminate, the only possibility is to produce this. But if I switch the possibility, for example, if I do CH3, this is the same thing. And if I have here Br instead of hydrogen on that position, on this position, and put this CH3 here, this also could give this. But the problem is it could have different other compounds. So let's see what other possibilities are there, or is this the only product we can get? So let's check this. This is one beta carbon. This is another beta carbon. This is another beta carbon. There are three possibilities for this. So if I just use one of this, right, so I would just get CH3 2 C CH2. That's good. You get that one. If I use one of this as well, I would get still the same. If I use one of this, I will still get this the same. So there are two possibilities or two types of alkyl halides we can use to produce that. So this is how you'd just generate. So this as well as this can give this product. So that can also give this. So CH3, C, CH3, Br, the alkyl, the halide in the middle carbon also can give the same product as we already seen. Let me see on this one. For this one, let's say chloride compound for this one would be, for example, I can use CHH2 chloride, let's say. This alkyl halide, this is the alpha carbon, this is a beta carbon. Therefore, that by elimination could give me this product. So I can suggest this as my starting material. This is called mostly retrosynthesis, to go back and suggest the starting material that could produce this. I can also put the chloride here and see what I can get. So if we put also ClH and CH3, this is the alpha carbon. Now, if you just eliminate this from this one, you'd generate the same product. So this is another possibility. Either you put the halide on this carbon, it doesn't really matter. You still get the same isomer. How about on this one? For this one, for example, if I put the chloride or bromide on that terminal carbon, it should look like, let's say it's bromine. This is the alpha carbon. This is beta carbon. So if you just use one of the hydrogens from here, you just generate that. Okay? So that's the possibility. The bromine on this one. So let's see here. Bromine here. 3 hydrogens on this and this. This also can give me the same alkene product because this is the alpha carbon. This is the beta carbon. There is a beta carbon here, but there is no beta hydrogen. So it doesn't complicate the product I get. So the only alpha beta hydrogens are on this, the 3 hydrogens. So one of them can be used still to give me that product. So even though there is a beta carbon, there is no hydrogen that can be eliminated. So exclusively I can get this. So all of the starting materials can give the required the required constitutional isomer. So this is retrosynthesis. So it's going back and suggests what alkyl halide would produce, the only product that is suggested in this. So we'll continue more on this. Okay, continuing our discussion on elimination reactions, I have these two compounds on the board, and the question is why A reacts fast in E2 mechanism. That means in the elimination reaction, A reacts faster than B. And it's asking you because if you just look at the alkyl halide, this is a secondary alkyl halide. This is also a secondary alkyl halide. Okay? So they are almost the same secondary alkyl halides, but at a different position. Why is in the E2 mechanism, in the elimination reaction, why A reacts faster than B? So the main important point is first to draw all the possible products that the E2 reaction gives you. For example, if we just consider an elimination reaction E2 of this one, if this is an alpha carbon right here, and this is a beta carbon, if you just consider and this as beta carbon, let's see what we would get. Obviously, there are other beta carbons as well, but let's see what the differences in these two products are. So if we were to eliminate this hydrogen and this bromine from the alpha carbon, the product you'd get, obviously E2 is a reaction you have to do. That means a strong base is implicated. So the product for that would be CH3, CH3. This carbon is losing that hydrogen, this carbon right here, the beta carbon. And you have CH2 on this you have CH and CH2, CH3. This is one of the products you could see from the top reaction, A. So usually you have to see, whenever you are asking the rate of reaction, why fast or slow, you should examine the starting material or the product formed. That's the only way you could tell whether something can go fast or slow. So now we are evaluating what products we get. In this E2 reaction, you would get from this CH3, two of them. So another CH, another CH right here, double bond, and CH, CH3. This is one of the products that's possible, right? So if you just look at this in the way I have them, you would have here a tri-substituted alkene. This is tri-substituted alkene. Here you have just a di-substituted alkene. Di-substituted alkene. So it is much easier for a reaction to form a more stable product, which would be goes fast. That's why it is going fast. And that is a di-substituted, a less stable one. So the less stable cannot form very fast, because the less stable is not something the reaction likes to do. So that's one of the reasons. So if we were also to see a loss from this beta carbon if you just look at a beta carbon from this, the product you would get is, this is still for A, but a possibility from another beta carbon, the product is that CH3, 2, CH, CH, CH2, CH3. This is by losing one of the hydrogen from here and the Br. In the second one, also the other possibility in this one is if this one of the beta hydrogens are taken off, you would get CH3, 2, CH, CH2, CH, CH2. In both cases, B always gives you a very unstable one. This is a very unstable terminal alkene. Terminal, unstable. So the reaction will not be fast to form this. But in this case, it is at least a di-substituted. Di-substituted. So in the reaction, A, in both cases, whichever beta carbon you're considering, you would form faster in the A. So the equation is faster for A than for B. So that's how you evaluate with the stability of the alkene. So this is tri-substituted, it forms fast, it is more stable. So the di-substituted, lesser stable as compared to that, less stable, reaction goes slow. If you just consider other beta carbons and beta hydrogens, you'd get these two, di-substituted, better stable, more stable. Always it's relative. More stable, it goes faster. And for this, a terminal alkene, that's just a monosubstituted one. So it's less stable, and slowly formed, slow in the reaction rate. So this is how you evaluate. You can evaluate the starting material, or you could evaluate the product. So that based on the stability of the product or the instability of the starting material, that's how you would determine the rate of a reaction. So both are for E2 reaction. We'll continue our discussion on elimination reaction. I have this alkyl halide and a tertiary butyl oxide in tertiary butanol. This is the reaction. And we are going to do different conditions. The first one would ask us to just show the reaction mechanism. Obviously, if you just look at this, this is a primary alkyl halide. So the primary alkyl halide exclusively undergoes an E2 reaction. So the mechanism for this should be an E2 mechanism. That means abstraction of the hydrogen and the leaving group leaves simultaneously. So this is E2. Remember now what I said. You have a very strong base. You have an alkyl halide, which is primary, not tertiary, which doesn't make a carbocation. Therefore, this reaction goes through an E2 mechanism. So this is the alpha carbon, and this is the beta carbon. So the hydrogens are over here. So what I'm going to do would be hydrogens on a beta carbon. So one of the hydrogens would be abstracted by the electron, the base. That's a mechanism. While this is being abstracted, this bond with a pair of electrons would form here and this leaves. So what I just showed is the reaction mechanism. So the product for this through that mechanism is 1, 2, 3, 4, 5, 6, I think. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 is right here. So this will give you a terminal olefin. So this is just a monosubstituted olefin or an alkene. Olefin is an old naming, but anyways, that is a terminal alkene. So in the second condition, it's asking you what would be the rate. Would the rate increase or decrease? So here, rate is what the question is. Would the rate increase or decrease if we use, instead of tertiary butanol, which is an alcohol, but instead of that, if we replace it with DMF, if you remember from our substitution reaction, is a dimethylformamide. Dimethylformamide is not a protic solvent. So if you just change this protic solvent by a protic solvent, the rate for E2 reaction would increase. Protic solvent, reason being, you are using non-protic, aprotic solvent for an E2, rate increases. So aprotic solvents for an E2 reaction, rate increases. So now we are also learning what the conditions for the mechanism is. E2 requires strong base. Obviously, we have tertiary butoxide. We have a strong, bulky base. But now we had a tertiary butanol given. If you change that, the rate of the reaction would be increasing. Rate increases. Okay. In the third question, what would be the rate if the concentration of the tertiary butoxide is decreased? Concentration of tertiary butoxide, the base, that is, decreased. What would happen to the rate? So first you have to write the rate law for this. Rate equals, this is an E2 mechanism. E2 mechanism involves both the base as well as the alkyl halide, which is 1, 2, 3, 4, 5, 6 Br. So that's the rate for E2 reaction. So the question is, if the concentration of this is decreased, obviously the rate would decrease. If this is going down, rate will decrease. Obviously, it will decrease. It will be affected because it depends on the base as well as the alkyl halide concentration. What would happen if the base is changed to the rate? Base is changed to a hydroxide base. Hydroxide is a very strong base. It's an inorganic base. So I would say that the strength of the base is increased, so the rate should increase. Rate increases because you have an hydroxide stronger base. Hydroxide is a very strong and small base, that would be rate increases. How about if we change, instead of a primary, if we start with alkyl halide, which is a secondary alkyl halide, what would happen to form this? So what happens in this case would be if the rate for this one would be for the secondary one, you are also creating more than one product, remember here. So the rate should be, if you just use this, you are creating, for example, this is a beta carbon, this is another beta carbon. So you are generating two products. One is this, 1, 2, 3, 4, 5, 6, plus one, 2, 3, 4, 5, 6, not this product. So you are generating to this two competing reactions. Definitely the rate would be decreased if you were to form this. So this is the only product we have in this case, but the rate of the reaction, if we are just considering not the product, but the rate of the reaction here, it's generating a disubstituted alkene. Disubstituted, and this is monosubstituted alkene. So basically, if you are using bromine, the rate that this thing is converted into product would get faster, because this is a disubstituted stable alkene. So the rate of the reaction would increase. So together with this, you are also creating this one. So the conversion of this into these two would be faster. But major product that would be formed would be also this. If you are asked what would be the composition of this would be qualitatively, this is major and this is minor product, because a disubstituted alkene is more stable, so you would be forming more of that. How about if you change bromine into iodine? Here, if you just use iodine instead of bromine, the rate would increase. Iodine rate increases because it's a better leaving group. So if you just compare the leaving groupability, fluorine is less than chlorine, chlorine is less than bromine, bromine is less than iodine. So iodine is the most fast leaving group. So as a leaving group, iodine is much better, therefore rate would be increased. So if you just look at fluorine, chlorine, bromine, iodine reacts the fastest. So if you change this into iodine, the rate of the reaction would be much faster. So we'll continue more on this. Okay, continuing our discussion for the elimination reaction. We have a problem here which shows the cyclopropyl system, a halide obviously, and the potassium tertiary butoxide, strong base, as a base and undergoing elimination reaction. In this problem, you would see that the presence of two beta carbons, that means two beta hydrogens and an alpha carbon, makes it possible that you'd be generating two products. Obviously, you could see in the product side, two products are formed. In these two products, you see that this is a disubstituted exocyclic alkene. This is an internal alkene. So remember now, I'm just introducing new terminology here. This is exocyclic bond. It's out of the cyclic system. Here it's internal in the cyclic system based on the elimination of this beta hydrogen or that beta hydrogen. So that would give us these two products. The exocyclic one is a disubstituted because you have hydrogens. So these are the alkyl groups. So it's a disubstituted. The internal alkene is a trisubstituted because you have this alkyl group and that alkyl group, and you have hydrogen here. So this is a trisubstituted alkene. This is disubstituted alkene. So the question is, if you just look at here from Saytzeff rule, the major one should be B, right? Because a more substituted alkene would produce a more stable alkene. But why is the difference now? If you just look at here, a major one is A, but a minor one is B. So it's reversed. So the main explanation we could give to this is very simple. The internal alkene or the internal alkene is very hard to make. If you remember, angle strain and torsional strain becomes more severe as the ring system is more gets more and more smaller. So here you have angle strain, torsional strain, torsional strain. So in a ring system, as small as cyclopropane, it's very hard, it's very unstable to have a double bond inside a very small ring because of angle strain and torsional strain. So it becomes a minor product. So it's more than just in a straight chain system, it is easier to rationalize with Saytzeff rule. But in this case, since there is another factor which makes the angle strain and torsional strain in the small ring system to create a double bond, that would be very unstable. So this would be very unstable, and this is a major one, a stable product. So if we are asked, for example, further between these two, which one would react vigorously in hydrogenation, this would react immediately to get saturated. So if you further take this and hydrogenate this, meaning that to create this versus if you have this hydrogenation to create this same product, the reaction in the lower portion is very fast because this is very unstable than the top one. The top one is relatively stable. So also in this reaction to get to that, but in the top reaction, in the elimination reaction, you would create major products, this one, because this one is much more less stable because of angle strain and torsional strain. This is hydrogenation reaction to get a saturation of the double bond. Fast, this is slow. Okay, we'll continue with more on alkene or elimination reactions. Okay, continuing our discussion. Here we have two problems where it's asking you to draw major and minor stereoisomer products. So whenever we form an alkene compound, or as a result of elimination, when you form a double bond, there is a possibility of stereoisomerism. That is to say that during the elimination you can form a cis or trans compound. Okay, let's see. It's asking us to give obviously the major one. So in this case, you have an alpha carbon, and here you have a beta carbon. So this would give you a product which looks like CH3, CH2, CH double bond, C, H, and a phenyl group. Now, we haven't drawn this in a stereoisomeric form, so the first thing, once you have this can exist as two stereoisomers, the double bond. That means if I draw a cis, CH2, C, this is phenyl up, and H down, and H down. This is one of the stereoisomers of that alkene. Definitely, you could also produce another one, which is CH3, CH2, and here is hydrogen, here is the phenyl group. So you have two products from this elimination reaction. So what we understood from both are di-substituted. So this, in terms of to be a major and a minor, stability of the alkenes is still important. We have said that if you have two bulky groups like this in the same side, there is always a steric clash between these two bulky groups. So this would not be a major product. If you are just randomly reacting this would be minor. The major is the trans compound, major. So this is cis, this is trans. So those are the products and the two stereoisomers, cis and trans stereoisomers. Obviously, we used a potassium hydroxide base. And in this one, we are using sodium ethoxide. This is called sodium ethoxide base. Now we have a beta carbon right here, and these beta carbons are equivalent, so we have only one, because this, if you just consider this one, it will be the same because it's symmetrical. So there are two hydrogens on this, let's say, and the elimination reaction would give so it would be 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So that's one of the products, but from this elimination you could also have this product as well, meaning that in the this would be another product. 1, 2, 3, 4, 5, 6, 7. So the hydrogens are this, the hydrogens are this. So two products plus. And so if I were to decide between these two, still those are doubly substituted, the same substitution pattern, double alkyl, but here this is a trans, and here this is a cis. So I would say the major one still would be a trans compound. This would be a minor product. So this is a relative term. So you could get, I'm not sure, 70-30 or 80-20, something like that. But qualitatively, you know that the trans compound is a major product. So when we say stereoisomers for an alkene, we meant that it is cis and trans. Okay? So we'll continue more on elimination reaction. Okay, so for an E1 reaction mechanism, we have three problems. So this problem is asking you to give a major product and a minor product from this E1 mechanism. So it's obviously natural to say this substrates or this alkyl halides would undergo an E1 is because they could produce a very stable carbocation. So let me just draw the intermediate carbocation before the actual elimination happens. So this is how it looks like. So that carbocation is tertiary, so it makes sense that it goes through an E1 mechanism. Here for this one, we have carbocation, which is tertiary as well. Here for this one, we have two metal groups. So that's what it looks like. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So these are the corresponding carbocations. So now, in order for the elimination to happen, this is an alpha, a beta carbon. This is one beta carbon as well. For this one, you have this beta carbon and this beta carbon and this beta carbon. Actually, I think this one and that one are equivalent, so I will just leave one of them. And also for this one, we have this beta carbon and one of this are the same, so another beta carbon. So this is what the elimination should give us. So this should give us two of them. So if I use this hydrogens right here, the elimination product should look like a double bond right there, CH3, CH3 right there. One of the products would be like that. But if I use this hydrogens, one of the hydrogens, only one hydrogen here, the product looks like CH3, CH3. Those are the two alkene compounds that could be produced by an E1 mechanism. So if you just look at this is tetra-substituted alkene, because this is alkyl, this is alkyl, CH3, this is tetra-substituted, tetra-substitution. For this one, there is one hydrogen here. This is tri-substituted. This is tri-substituted. So between the tri-substituted and the tetra-substituted, by this step, this would be a major stable alkene. So this would be minor. Okay? Okay, let's continue on this one. For eliminating from this beta carbon should give me that product And also, if I eliminate from this one, it should give me that, right? So if you just look at this alkene, this is our hydrogens. This is a di-substituted alkene. But this one, this is CH3, so this is a tri-substituted alkene. So the tri-substituted alkene is major, and this is minor. Okay, how about for this one? For this one, we have, if we eliminate from this one, we get this plus, if I use one of this, it would be that. I think it's true. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So if you just look at this, this is tri-substituted, and this is di-substituted. Therefore, the tri-substituted is major, and this is minor. So those are the products that we would get with the E1 reaction. So major and minor is determined by Saytzeff Rule, where more substitution would give you a more stable alkene. So we'll continue with another video on the elimination reaction problems. Thank you.